Hello everyone. Let me introduce easy guide to understand RecurDyn contact. This is part 2. So, if you didn't watch part 1 yet, please watch it first. This is the index of this seminar. In part 1, I introduced contact mechanics and the basics of RecurDyn contact briefly, and I introduced the types of RecurDyn contact and some basic functionalities. In this part 2, I will explain the general process of contact modeling step by step. Finally, I will show some case studies to demonstrate how to determine the contact type and how to use the parameters. Now, let me explain the process of contact modeling in RecurDyn, using the information and parameters I mentioned earlier. Especially, I will explain technical tips for contact modeling and parameter tuning. First, choose the type of the contact entity according to the geometry and contact type. Step 2. Select base and action geometries. Step 3. Create contact entity. Create the surfaces if needed. Step 4. Set the facet parameters. Step 5. Set the contact parameters. Step 6. Set the other optional parameters. Step 7. Simulate and tune the parameters. Let me explain the detail of each step from the next page. This is a simple guide to choose the type of the contact entity. First, check if a body has 3D motion. If yes, use 3D contact, or if not, use 2D contact. Check if the geometry shape is complex. If yes, move to the next branch. If it is simple, then consider using primitive contact. For 2D contact, also check if the geometry shape is complex. If the geometry shape is complex, then use geox curve contact. If it is circle, consider using primitive contact. If any of the contact bodies is flexible body, then geosurface contact is the only option. If both of them are rigid, then move to the next branch. If the radius of the surface curvature is small, then use geosurface contact. If it is convex or flat surface with large curvature, then you can use solid contact. Step 2. You need to select the base and action geometry. Let me introduce the tips to select the action geometry. First, select the geometry whose contact area is smaller as action. It is advantageous to use the denser facets for action geometry, the surface whose contact area is small, like this. Second, select the geometry with a smaller radius of curvature as action, like this. And select the geometry which has the larger motion as action. Step 3 is about creating a contact entity for the base and action geometries. If needed, it is efficient to create a surface for contact instead of using entire body. For example, in case of this Geneva wheel, simulation speed can be 3 times faster by using a surface instead of the entire solid. For example, these surfaces are used for contact, so instead of using entire body, you can create a surface using these faces. Let me explain how to create the surface briefly. First, double-click to enter body edit mode. Then, click Face button from Ribbon Control. Next, select a solid geometry. And select Add Remove button here. And select the faces of the solid geometry. Click OK, then a surface entity is created. Step 4 is about setting the facet parameters, the size and shape of the facets significantly affect the accuracy and the simulation speed. The dense facets are needed, especially where contact occurs, to represent the original surface well. Plane tolerance factor is the most frequently used parameter. You can see the difference with the different value for the plane tolerance factor. This used 3 and this used 0.2. This has the dense facets. To generate a stable contact force, the smaller facet size is desired. Usually, max facet size factor is used. This one. This max facet size factor is also used for a flat surface. As you can see, with 10, there are only few facets. But if you use smaller max facet size factor, then many facets are generated. And you can see for the flat surface, several contact forces are detected. Step 5 is about contact parameter settings. First, stiffness coefficient can be determined based on Hertzian contact theory. But in many cases, this parameter is tuned frequently based on various factors. Second, damping coefficient, 1 over 10,000 of the stiffness coefficient is often used as default, but this is tuned frequently too. Third, friction is determined by experiment or theoretical data. For the threshold velocity, you can use the default value in most cases. Number 4 is stiffness exponent. It is 1.5 according to Hertzian contact theory, but it is okay to use the default value 2 as it is. Number 5, you can use the default value for the maximum penetration. The default value is automatically decided according to the size of the geometry. Number 6, it is worth remembering the maximum step size factor. If the locations of two bodies are far apart, 10 is recommended. But if two bodies are very close to each other, then 1 is better. If you use big maximum step size factor, simulation can take long. So, this value needs to be tuned carefully. Step 6 is about the other optional parameter settings. Node contact was explained earlier. In general, you can use the default settings as they are. Please note that node contact is checked by default for action geometry only. Usually, you don't need to use the node contact option for base geometry. Normal direction means the direction of the surface that is used for contact. For example, in this image, the external surface of the cylinder is used for contact, the outside. So, in the image on the right, the direction setting is incorrect because it shows that internal surface of the cylinder is used. If there are balls inside the big sphere, the internal surface of the sphere must be used. So, please check the normal vector direction carefully. There are two options in the advanced setting dialog, smooth node contact and CPM. I already explained what they are earlier. The default of smooth node contact is off. Use this option for the tight contact between a shaft and a hollow cylinder, for example, or if the contact point moves along the large surface. The default of CPM is on, but it must be off if there are many contact points and the directions of the contact forces are not uniform. For example, in case of the tight contact between a shaft and a hollow cylinder, you should check off CPM. Number 3 is edge contact. The default is on, but the simulation speed can be improved if this option is off. But please remember when this option must be on. I explained it earlier. If you are not familiar with that, it is recommended to use the default setting, which is on. Number 4, the number of max contact points doesn't affect the simulation at all. 100 is recommended for this parameter, but please remember you can increase the simulation result file size. Force display is the option for post-process. The contact force vector is displayed during an animation. The last step is about simulation and parameter tuning. I already mentioned several parameters require tuning in the previous pages. Contact model has many uncertainties, various geometric shapes, material properties, surface roughness, lubrication condition, and even numerical limitations. In general, users need to tune the contact parameters after simulation, and the correlation with experimental data and parameter tuning are very important to obtain the accurate results and run faster simulation. First, run simulation, then review the simulation results and calculation speed. Based on that, there are several ways of parameter tuning. First checkpoint is the occurrence of the contact event. If contact doesn't occur or one body passes through another one, using denser facets or increasing the maximum penetration is recommended. The normal directions of the contact surfaces must be checked also. Second checkpoint is penetration. If the penetration is excessive or one body passes through another one, increase the stiffness coefficient or stiffness exponent. If the contact directions are not uniform, then check off CPM, because CPM works as if stiffness is decreased. For the precision machine or thin material transportation machine, such as printers, the penetration itself is important. In that case, calculate the load and find the appropriate stiffness to generate the expected penetration. Third checkpoint is restitution characteristics. If the body doesn't rebound or rebounds excessively, adjust the stiffness coefficient, the stiffness exponent, or the damping coefficient. Please note that you need to change the damping coefficient according to the change of the stiffness coefficient like this. If you increase stiffness by 100 times, you need to increase the damping by 10 times. If you decrease stiffness, then you need to decrease the damping in the same manner. If the logarithmic decrement ratio is given, you need to find the damping coefficient through the repetitive simulations. First checkpoint is step size. During the contact model simulation, sometimes the solver step size becomes too small, so the simulation either takes long or stops. Usually, the bigger stiffness is used, the smaller step size becomes. So, using smaller stiffness coefficient or increasing the stiffness exponent can make the solver use the bigger step size. You need to check the maximum step size factor also. If the accuracy is good enough, you can use 1 for the maximum step size factor. In many cases, setting maximum time step in solver setting less than or equal to 0.001 can make the simulation stable, so the simulation speed gets rather faster. This checkpoint is smooth contact force. The direction or the magnitude of the contact force sometimes oscillates because of the numerical reasons. In that case, use denser facets in the area where the contact occurs or use the smooth contact option. Using smaller stiffness coefficient also can reduce the oscillation of the contact force. I have explained contact mechanics and basics of RecurDyn contact, and I introduced the types of RecurDyn contact and contact parameters, and the general process of contact modeling. This is the last chapter. I will introduce practical case studies to show you how to build the contact models and tune the contact parameters for them. The first model is a CAM system. This model uses 4-geo curve contact. Since there is no motion in the depth direction, and the contact force in the depth direction is not important, a 2D contact was used that is much faster than 3D contact. So, a curve segment is used instead of facet. It means The curve is divided into 200 segments for simulation. To get the smooth contact force, the smooth node contact option was used. For your information, the end time of the simulation of this model is 2 seconds and the calculation time is 6.6 seconds. For 2D contact, the normal direction for contact must be checked before simulation like this. And these are the animation and plot results. Here is an example of ball bearing. There are 10 balls. The internal surfaces of the bearing are created as 4 arc revolution surfaces. So there are 40 contacts between 4 arc revolution surfaces and 10 balls. A primitive contact called sphere to arc revolution contact. It was used for fast and accurate simulation. Since the contact occurs from the initial state, maximum step size factor is set to 1. This is the simulation result, and this curve shows the vertical displacement of the outer ring. This is a linear guide. The red body moves along the steel rail. In this model, the red body is the action body because its motion is larger than the rail body. It is inefficient to use the entire bodies for contact. So, the partial surfaces are created as face surface for contact, like this. With the default facet settings, the facets of the rail have long shape. So, max facet size factor is used. Please check the plane tolerance factor and the maximum facet size factor for this model. This is a TV stand. There is a rubber non-slip pad under the bottom of the TV stand. One geosurface contact is used. Instead of using the entire body, only the surface of the non-slip pad is created and used for contact. Since the non-slip pad is flat surface, max facet size factor needs to be used. There are many contact points, and the directions of the contact forces are uniform, so CPM is used. This is a cycloid drive. This is often used in robots in the speed reducers with high gear ratio. 3 geo contacts are used. In this model, the face surfaces are used instead of the entire solid geometries. If the entire solids are used, the simulation speed will be much slower. In this model, CPM is not used because the contact points have different directions. For the sliding shaft contact in the center image, smooth option is used. This is the simulation result of the cycloid drive. This is the last example. This simple gear system consists of various gears. 5 contacts are used between each pair of gears. Again, face surfaces are used instead of using the entire gear solids. Since the contact force directions at the gear teeth are almost uniform, so CPM is used. This is the simulation result. Even for this kind of gear system, the simulation time is very short, and the simulation result is good enough. I hope this seminar helps you to get the good results like this. I have explained basics of contact algorithms, types of RecurDyn contact, and contact parameters. The best way to understand them is to create as many models as possible and try to tune the parameters on your own. Contact. You can use it well too. It is not difficult. When you have free time, why don't you create and simulate this kind of billiard model? Yes,